The strongest story in space exploration is not one rocket launch, but a pattern. Missions are becoming our distant senses. When a spacecraft leaves Earth, it is more than metal and fuel. It becomes a remote pair of eyes, ears, hands, and sometimes even a laboratory. That is why robotic missions stand out so strongly. They can go where humans cannot yet safely live. Wait through silence, survive harsh radiation, and keep working long after the first dramatic moment is over. Think of a Mars rover. It does not simply roll across a desert. It studies rocks that may preserve clues from a wetter ancient world. It drills photographs, measures, listens, and sends everything home at the speed of light. But even light is slow across space, so the rover cannot be driven like a toy car. Engineers give it careful instructions, then wait. This is the quiet magic of modern exploration. A mission can turn a distant place, from a dot in the sky into a real landscape with weather chemistry. History and unanswered questions, what is known is powerful. Robotic spacecraft have mapped planets, tasted atmospheres, flown past comets, entered orbit around giant worlds, and landed on moons and asteroids. They have shown us that the solar system is not a set of simple balls circling the sun. It is a collection of active worlds. What remains uncertain is just as important. A spacecraft can find ingredients, patterns, and clues, but it rarely answers the biggest questions alone. Was Mars ever habitable for long periods? Do ocean moons have the right conditions for life? How common are Earth-like environments beyond Earth? The takeaway is simple. Space missions matter because they extend human presence without needing human footsteps. They are how curiosity learns to travel, and every mission begins with the same promise somewhere far away. Silence is waiting to be measured. The most ambitious Mars mission is not just to visit the planet. It is to bring a small piece of Mars back to Earth. Mars sample return is one of the hardest ideas in planetary science because it asks several missions to behave like one long relay. First, a rover selects rocks that seem scientifically valuable. Some may record ancient water. Some may preserve the chemistry of an environment that once could have been habitable. The samples must be sealed, carefully stored. Located again, launched off another planet, captured in space, and returned safely to Earth. That chain sounds simple only until you imagine doing it with no repair crew, no nearby workshop, and minutes of communication delay between Earth and Mars. Why bring samples home at all? Because laboratories on Earth are far more powerful than anything we can send on a rover. Instruments here can examine tiny structures, measure ages with extreme precision, and test samples again as technology improves. The moon rocks returned by Apollo are still being studied today. Mars rocks could become a scientific archive for generations. What is known is that Perseverance has been collecting and sealing selected Martian samples. Scientists know those samples could help answer questions about Mars as a planet, how it changed, how long water lasted, and whether any ancient environments were friendly to life. What is uncertain is the best way to complete the return. Mars sample return has faced cost design and schedule challenges, and space agencies have been reviewing how to make the plan more practical. That uncertainty does not make the science less valuable. It shows how difficult the achievement would be. The fascination is partly scientific and partly human. To bring Mars home would be to cross a threshold. For the first time, the story of another planet could be studied not only from afar, but in our own laboratories. A handful of dust could become a library. And the next chapter depends on engineering as much as wonder. The next great step in exploration may not point toward a planet at all. It may point toward a moon wrapped in ice. Europa, one of Jupiter's large moons, is one of the most intriguing worlds in the solar system. From the outside, it looks frozen and hostile. But the evidence suggests that beneath its icy crust, there is a global ocean of salty liquid water. That does not mean life is there. It means Europa has one of the conditions scientists care about most when asking where life could possibly exist. A mission. Like NASA's Europa Clipper is designed around a careful idea. Do not claim too much, but measure the right things. Instead of landing and drilling through ice, the spacecraft is built to fly past Europa many times while studying its surface gravity, magnetic environment, and possible exchange between the ice and the ocean below. The goal is not to announce life. The goal is to ask whether Europa could support it. That distinction matters. Science moves best when the question is sharp. Europa has water energy from Jupiter's gravitational pull and chemistry that may be interesting. But the thickness of the ice, the composition of the ocean, and the movement of materials between surface and sea are still uncertain. Those details decide whether Europa is merely fascinating or truly promising as a habitable environment. Why does this matter for exploration as a whole? Because missions like this expand the map of possibility. For a long time, the search for life followed sunlight. Europa reminds us that habitability might exist, far from the warmth of the sun, hidden under ice powered by tides, protected in darkness. The memorable takeaway is this: exploration is not only about reaching new places, it is about learning which questions are worth the next journey. Some missions bring the universe closer. Others reveal that the next frontier may be underneath a frozen shell,